we are going to explore the concept of recursion and its implementation in the C programming language. And here the ultimate key for understanding recursion. Recursion is typically defined as the process of representing a problem or the solution to a problem in terms of a simpler version of itself. And for this strategy to work, we are going to make use of three fundamental terms of recursion: the starting point, the recursive calls, and the base case, which will tell us when to stop. This concept of recursion should not be confused with that of iteration, which is something we will discuss later. For now, we are going to understand these definitions of recursion through an example. In mathematics, there's a common calculation known as the factorial, in which the number we want to calculate the factorial from is multiplied by all its successors until it reaches the base case 1. For example, the factorial of 6, or 6 factorial, equals 6 times 5 times 4 times 3 times 2 times 1, which equals 720. The formalization of this procedure is what follows. We can quickly see almost the pseudocode of our implementation in C. Before we implement this code, just bear in mind what we are trying to achieve. For calculating the factorial of 6, we know we have to multiply 6 times the factorial of 5. But what is the factorial of 5? Well, 5 times the factorial of 4, and so on and so forth. But notice we do not have to worry about all these operations. As opposed to iteration, in recursion we program with a style called declarative, in which we do not have to specify all the details involved in a certain computation, but we just specify to the computer what the definition of the objective is and let it do the rest. For the implementation of the factorial function, I'm going to first add the appropriate headers. Next, the function prototype. Now the main function. With its return code. We're going to use a positive integer and we are going to print the result. Now we are going to implement the body of the function. We're going to first consider the base case. And finally, the recursive call. And we're done. Now let's test it. And sure enough, we have the result. Before moving forward, let's retake some of the differences between recursion and iteration. First of all, the control structure in iteration is always a loop, while loop, for loop, or do while loop, whereas in recursion we use self-function calling, or recursive calls. Local variables in recursion are not relevant unless they are passed by reference, but since we are doing function calling, every call will create new slots of memory for the new variables. For this reason, also variable updating is not usually required. As we already saw, in recursion we just declare the objective we want to achieve and let the computer handle the process by itself, contrary to iteration, in which we have to specify all the steps involved in the process. This is also the reason why generally a program with recursion is much shorter than another using iteration. And finally, we are going to talk about how recursion occurs in the computer's memory. Here we have a visual representation of the computer's memory when dealing with recursion. If we want to calculate the factorial of a number, then the computer asks for another slot in the stack to calculate the nth minus 1 factorial, and so on and so forth, until the base case is hit and the stack starts to recover space. So for example, if we want to calculate the factorial of 4, we ask for a slot in the stack to calculate the factorial of 3, and then of 2, until we hit the base case 1, which starts the process of freeing memory. Before getting into complexity analysis, let's first look at one more example of recursion, and also the types of recursions that we can use. The Fibonacci series 0, 1, 1, 2, 3, 5, 8, etc. begins with 0 and 1 and has the property that each subsequent Fibonacci number is the sum of the previous Fibonacci numbers. Here we have its formalization. Fun fact, Fibonacci and factorial are called primitive recursions because they can also be calculated using iteration. So well, let's implement this in the C language. As in the factorial program, I'm going to first add the appropriate headers. The function prototype, and the main function. What we are going to do is to print until a certain position of the sequence. Let's say the 10th position through a loop. Now we are going to implement the body of the function. First, we are going to consider the base cases. And finally, the recursive call. And it seems we're done. Let's test it. And sure enough. Finally, we're going to talk about a type of recursion called tail recursion. The difference between using this particular form of recursion against not using it is that in tail recursion, calculations are performed first, and then the recursive call is executed, passing the result of the current step to the next recursive step. The return value of any given recursive step is therefore the same as the return value of the next recursive call. We can see in the examples two functions achieving the same goal, the summation for adding the first n integers. On the left, note how every recursive call has to complete before the C compiler begins to actually do the work of calculating the sum, whereas on the right, in the tail recursive case, with each evaluation of the recursive call, the tail sum function is updated. Which of both is more efficient? Well, unfortunately, things like this depend entirely on the particular implementation of the compiler. C compilers do not normally give any guarantees about what optimizations will and what optimizations will not happen in each particular piece of code. You actually have to compile it and see for yourself. In the meantime, we're going to implement both functions to get a better understanding of the differences. First, we are going to implement the non-tail recursive form of the function. So let's start. The prototype of the function, the main function, and I'm going to print the result. Now the function implementation. Consider the base case. The recursive call. Very similar to what we have been doing. So let's test it. And sure enough. Notice that in this particular style, the syntax here, in the return statement, we still have to make a calculation before actually getting the result of the recursive call. In the tail format, we do not make any calculations after the recursive call. Now we are going to implement the tail sum function. So let's start. I'm going to use the legacy underscore naming style. Again, I'm going to print the result. The body of the function. And we can test it. There we go. So notice that in this particular style, calculations are made in the arguments of the recursive call. This recursive call is actually the final operation of the entire function. At last, what we were all waiting for, computational complexity. First, a fast review of different complexities and the big O notation. Here we have a graph showing the number of operations versus the number of elements with different magnitudes of computational complexity. Remember, we want to stay in the low slope region, avoiding quadratic-like complexities and, of course, exponential complexities. So, how complex an algorithm with recursion is? Notice how binary search and merge sort manage to stay at a reasonable complexity. The case of selection sort is different, but still, we know the implementation of these algorithms using iteration have similar complexities as with recursion, and since iteration normally could equate to messy code, we can implement recursion with reasonable confidence. But not all algorithms exist inside this attractor. Recursive Fibonacci elevates the complexity outstandingly and performs radically different than its equivalent using iteration. So given this danger, when is it convenient to implement recursion? Well, unfortunately, in C, which is an imperative language by design, recursion is fairly expensive compared to iteration because it requires the allocation of new stack frames. So in case of doubt, use recursion only to solve problems that can be broken into several subtasks, like for example the divide and conquer strategy. Remember, recursion is implemented as a method that calls itself to solve subtasks. Let's talk more about the divide and conquer strategy, which consists in dividing the problem into two or more instances of the same problem, solve those instances, and obtain the general solution to the problem by combining the smaller solutions. Sounds like an ideal application for recursion. This strategy uses a top-down approach and is widely used in a variety of fields in computer science, including sorting algorithms and syntactic analysis, but also in computational science for solving discrete Fourier transforms and matrix multiplication. Let's analyze some interesting details regarding merge sort. At this point, you are surely asking, but why merge sort? The answer is, because why not? Well, jokes aside, I'm not going to deal with all the particular details of the entire implementation of the algorithm, but rather we are going to look at the recursive function. Well, the function receives an integer pointer which has the address of the first element of the array of integers we are going to sort, and the size of the list. The base case consists in that if we already have just one element to sort, we consider that element as sorted, which will be the simplest case. We simply do nothing, just return. Next, we start dividing the list by halves and assigning memory for each half. We go from the first element to the one in the middle minus 1 for the first sublist, and from the middle element all the way to the end, again allocating memory for each list. We use the new memory spaces to accommodate both lists and finally make the recursive calls passing both halves of the present list until both end up with less than 2 elements to sort, so that finally both lists can be combined. Remember, we use pointers because we want to have the reference to the original memory areas within the same function and for the merge function to use. Specific memory sizes can be assigned as demonstrated. Here we have a visual representation of what the algorithm is doing, effective and efficient, thanks to the magic of recursion. Another good example and application of recursion is the binary search tree, a data structure in which each node has at most two children, which are referred to as the left child and the right child. These are a particular type of data structures that store items, such as numbers or names, in memory. They allow fast lookup, addition and removal of items, and can be used to implement either dynamic sets of items or lookup tables that allow finding an item by its key. For example, finding the phone number of a person by name. Let's look at a particular example to better illustrate recursion in this case. I'm going to implement the function for searching the binary tree. I'm going to start by specifying the return type, which will be a pointer to a node. We will receive the key we are looking for and its corresponding leaf. I'm going to make sure we are not getting any error in case the key does not exist. Okay, so if we found the key, we're going to return it. Else, if the key we are looking for has a smaller value than the key of the leaf in which we are now, then we are going to search for the key in the left side of the tree. In the other case, we're going to search in the right side of the tree. And there we have it. There exists yet another type of recursion, which is called mutual recursion, a form of recursion where two mathematical or computational objects, such as functions, are defined in terms of each other. Let's look at an example. So what we are going to do is to create a function or two functions that tell if a given number is odd or even, using the concept of mutual recursion. So we're going to test this with a number, let's say this one. And what we are going to do is to check if the return value of the function odd given this number is 1, then we're going to print that this number is odd. In the other case, that the number is even. So let's implement the functions. First, we're going to implement the odd function. So we're going to check for the base case if the number has reached a value of 0, return 0 for this function, and else we're going to call the even function, making a subtraction of the current number. Now, for implementing the even function, we'll receive this number, and we check also if the number has reached 0. In this case, we return 1, indicating that the number is odd, and in the other case, we make the recursive call of the other function, making the same subtraction. So we can test it. Here we have the result. We can test with perhaps a simpler value, let's say 2, or smaller value. And sure enough, it is even. Other interesting applications of recursive programming is the simulation of complex systems. For example, for the generation of self-similar patterns, such as fractals. Some examples are the Sierpinski triangle, a fractal with the overall shape of an equilateral triangle, subdivided recursively into smaller equilateral triangles. The KOCH snowflake, which can be constructed by starting with an equilateral triangle, then recursively altering each line segment by first dividing the line segment into 3 segments of equal length, then drawing an equilateral triangle that has the middle segment from step 1 as its base and points outward, and finally removing the line segment that is base of the triangle from the previous step. We also have fractal trees with similar characteristics. Here we have the recursive draw fractal line function implemented in the C language for the KOCH snowflake. Note that this implementation uses tail recursion, since no calculations are made before the recursive call, making the function to update itself rather than to wait for specific values to be returned. Considering that, the base case is then implemented based on the order value, which essentially controls the density level of the fractal. As for general culture, it is fun to know that the name of the operating system GNU Linux, the GNU part is a recursive acronym. It means GNU is not Unix, but the letter G in GNU stands for GNU again. If we expand, we get the same expression again and again. So, just a fun fact to know for software engineers. Now, a recap of what we have seen. Remember, all recursive algorithms consist of 3 parts. The base case, which is the condition that will allow the recursive calls to stop and return their respective value, or get updated. The recursive call itself, and the workout for getting into the base case. When trying to simulate mathematical functions, it is convenient to know its corresponding formalization for an easier translation into code. Recursion is programmed in a declarative style, which means we do not have to specify all the calculations made by the program, but let the computer do all the work. The cost of using recursion consists in the potential saturation of the stack, so this consideration should be taken before its implementation. Recursive functions that can be implemented with iteration are called primitive. Depending on the compiler, tail recursion could represent an optimized version of recursion. As with the example of Fibonacci, recursion could sometimes cause an algorithm's complexity to rise strongly, so think over before using it. Some examples we saw of algorithms using recursion are merge sort, binary search tree, mutual recursion, and complex systems. Finally, some readings that I recommend are the Head First series. They have a variety of books on several topics that, as said in a previous seminar, are very well and liked written. The topics include science, mathematics, and of course, a whole lot of programming and software development. Other very important literature is the C programming language, written by its creator, and Introduction to Algorithms by Thomas Corman. And that's it. Thank you very much and see you later.